All right, today we're going to pull back the curtain on a really clever piece of engineering called 4B5B line coding. Now, this is one of those secret ingredients working behind the scenes, especially in things like automotive Ethernet, making absolutely sure your data gets where it's going perfectly. So let's just dive right in. But first, let me ask you something. What if I told you that you could send a stream of data that is, well, perfect, no corruption, no errors at all, and it could still cause a total system failure? I mean, that sounds crazy, right? But believe me, it's a very real problem, and it's the whole reason something like 4B5B even exists. Just picture this. A long, never-ending stream of zeros, just one after another. To the device on the receiving end, this is like listening to a flat, continuous drone. After a little while, its internal clock, the thing it uses to time when to read the data, it starts to drift. It loses the beat. And once that clock sync is gone, the data just turns into garbage, even though not a single bit was actually wrong. So here's our game plan. We're going to start with why this synchronization thing is such a problem in the first place. Then we'll look at the 4B5B codebook, the solution. We'll get into the rules, walk through an actual example, and then talk about the hidden cost of making our connections so reliable. Okay, let's kick things off with the core issue, the synchronization problem, or how I like to think of it, why your system's clock needs a beat to dance to. So here's the absolute bottom line. For a receiver to make any sense of the bits coming in, its clock has to be ticking at the exact same rhythm as the sender's clock. It's taking little snapshots of the signal at very precise moments. If that timing is even slightly off, it might see a 1 when it should be a 0, or a 0 when it should be a 1. Game over. To stay locked in, the receiver is constantly looking for changes in the signal, what we call edges, where the voltage goes from high to low or low to high. These edges are like a metronome, constantly giving the receiver's clock a little nudge to stay on beat. A long, flat, unchanging signal has no edges, and that's when the clock starts to drift. It's why other systems like the CAN bus use tricks like bit stuffing to force these changes. But 4B5B, it has a much more elegant way of handling this. And that incredibly clever solution is called the 4B5B codebook. So what is it, technically? Well, 4B5B is what's known as a line code. For every 4 bits of your original data, it gets swapped out for a very carefully chosen 5-bit symbol. And this all happens right before anything actually gets sent out on the wire. The best analogy for this is to think of it like a special phrase book. Your system wants to send a simple 4-bit word, but to make sure it's understood correctly, it first looks up that word in its 4B5B phrasebook and sends out a slightly longer, but much clearer 5-bit phrase instead. So, how does this phrasebook actually work? What are the rules? Let's take a look. The real magic is in how the 5-bit codes were chosen. The engineers who designed this didn't just pick them at random. No. They specifically picked combinations that guarantee the signal will change. Like our source text says, every single 5-bit code that's used for data has a built-in mix of 1s and 0s. This one simple rule makes it literally impossible to send one of those long, flat, clock-killing signals. And here it is. This is the whole shebang. This is the codebook. On the left, you've got every possible 4-bit value you might want to send. And on the right, you've got the 5-bit symbol that actually goes over the wire. Check this out. Even the worst-case 4-bit code, 0000, gets turned into 11110. See how it has plenty of changes and ends with a 0? It's designed to break up that monotony. It's brilliant. Okay, theory is one thing, but let's make this real. We're going to take a byte of data and translate it step by step. All right, let's say we want to send the byte 11001000. First thing we do, we just split it right down the middle into 2 4-bit chunks, or nibbles as they're called. So we have 1100 and 1000. Simple enough. Now we grab our codebook. We look up that first group, 110, and bam, the table tells us its new identity is 11010. Then we do the same for the second group, 1000, which becomes 10010. All we have to do now is stick them together, and we get our final 10-bit transmission, 110101010. That's the signal that actually goes out onto the wire. But this awesome reliability doesn't come for free. Like any good engineering solution, there's always a trade-off. There is a hidden cost.
And that trade-off is literally in the name of the code. To send just 4 bits of our actual useful data, we have to send 5 bits across the physical cable. We're essentially sending extra stuff just to make sure the original message gets through loud and clear.
What this means is that the efficiency of the code is only 80%. We're using up 100% of our available bandwidth just to get 80% of the data rate we might expect. That extra 20%, well, that's the overhead. It's the price we pay for rock-solid, stable connection. So you might be thinking, wait a minute, 5 bits gives you 32 possible combinations. But we only need 16 for our data. What happens to the other 16 codes? Well, they're not wasted. The source material tells us that 8 of those extra codes are put to good use as special control signals, things like start of transmission or end of transmission. They help manage the whole conversation. And I want to be clear, this isn't just some abstract idea from a textbook. 4B5B is a foundational piece of technology and major standards you use every single day. Most famously, Fast Ethernet, or 100 base TX. It's a proven, battle-tested technique for reliable, high-speed communication. So, let's boil all of this down to the key things you really need to remember. Okay, number 1, the problem. Long, boring data streams of all ones or all zeros will kill your clock synchronization. Number 2, the solution. 4B5B uses that clever codebook to swap out 4-bit data for 5-bit symbols that are guaranteed to have changes, keeping that clock perfectly in sync. And number 3, the trade-off. This amazing reliability will cost you a 25% overhead in your bandwidth, but it's a price well worth paying for a stable connection. And that leaves us with one last thing to think about. We've just seen a really clear example of a trade-off between raw speed and guaranteed reliability. So my question for you is, where else in the world of engineering do we intentionally slow things down a little or add a bit of extra baggage just to make sure things are way more robust? It's everywhere once you start looking. Thanks for watching.